we were discussing the group of proper rotations in a two-dimensional plane, and I introduced the space, Hilbert space of square integrable functions over the group. If I take two functions, f1 and f2, this is the expression for their scalar product. And I probably did not mention yesterday explicitly that this scalar product is invariant in the senses we used for the case of a finite group. If you make a translation of the group element from the left by any amount or on the right by any amount, obviously this will not change. If you replace the group element alpha by 2 pi minus alpha, which means the inverse, then also it doesn't change. So this has all the invariance properties which we introduced when we discussed the finite group. Okay, so I just want to mention it. Yesterday I also told you how the left regular representation acts on functions in this Hilbert space, and the left regular representation and right regular representation, they coincide because it's an abelian group. Again, because it is abelian, the irreducible unitary representations are one-dimensional, and you know how they are described. For any positive or negative integer, including 0, there is a unitary irreducibility. It is one-dimensional, and the group element A of alpha is represented by this phase factor e to the power I m alpha. So we have a countably infinite set of inequivalent irreducible representations, a countable infinity. If you go back to the definition of the group SO2, and I will not write it again, it was defined as a group of real 2 by 2 rotation matrices, proper rotation. It is in the complex sense not irreducible representation. It is a direct sum of two of these things. Which ones? The defining representation of the group SO2, it was equation number 1 yesterday. It is in the complex sense, it is reducible, and when you reduce it, it must contain irreducible pieces. What does it contain? M equal to plus minus 1. It's just like going from linear polarization of light to circular polarization. The orthogonality completeness theorems in this continuous case are just the following statements. If you take two irreducible representations, m and m prime, and integrate product over the group, you get a Kronecker symbol, mutually orthogonal. And next, if you take a function on the group within this Hilbert space, it has a unique Fourier series expansion, which means it is expanded in terms of all the irreducible unitary representations. And you know the formula for getting the expansion coefficient. I write it in the symbol of the D's, and moreover, the squared norm of the function is the sum of the squares of the Fourier coefficients. So all well-known things about Fourier series representation for functions in the domain 0 to 2 pi can be viewed now in the light of group representation theory. They are related to the rotation group, proper rotations in the plane. Just one comment I would like to make. For finite groups, one of the statements we found yesterday was the number of irreducible representations is equal to the number of classes. Now that statement has to be modified when you go to a continuous group. You do not expect a one-to-one correspondence between irreducible representations and equivalence classes. The equivalence classes in the case of the group SO2, how many are there? As many as group elements. Every one is in a class by itself. So you have a continuous set of equivalence classes. The irreducible representations are a discrete infinity. Both are infinite, but one is a continuous and the other is a discrete infinity. So you can say that the fact that there are infinitely many inequivalent irreducible unitary representations, that infinity should be thought of as a dual to the infinite number of equivalence classes. Don't expect a one-to-one correspondence between the two. We will see this also in the case of 3 dimensions in a little while. Yeah. Comment. Yeah, please. Yes.
This is, you have started with functions on the group SO2.
Yes.
Then all these relationships are available.
Yes.
And what you showed yesterday, and this is well known.
Yeah.
As Fourier analysis.
Yeah.
Now what you showed yesterday is that such a Fourier analysis is available for any group.
Yes.
So this,
Yes.
the equation that is in the middle is what you called yesterday great orthogonal.
Yeah. Yes.
And there was a corresponding equation for every one of these equations that you had.
Yes, exactly. Yeah. Correct. So good that you emphasized all this. So we are not deriving new results, we are seeing well-known familiar results in a new language. The connection to group representation theory is being shown. Okay. Now we move on to the group of all rotations in the plane. What does it mean? What is it that is new compared to what we studied yesterday? We will allow improper rotations. So let me begin by giving you the defining representation of this group. It is called the group O2. So its defining representation consists of all real 2 by 2 matrices which obey two conditions. A transpose A should be 1, and that was one of the defining conditions for SO2 also. But now we allow the determinant to take both possible values, +1 as well as -1. So you can easily appreciate this group as a set splits up into two disconnected pieces. First, there are all those 2 by 2 matrices which are orthogonal, but for which the determinant is +1. That is yesterday's group, SO2. In addition, so I indicate it as a union, I must write all those matrices for which the determinant is -1. This is very elementary. I will introduce this notation. Sorry. I will explain everything as we go along. You should convince yourself, it is elementary matrix algebra, a 2 by 2 orthogonal matrix with determinant -1 can always be written in this way. So I want you to convince yourself that this group of both proper and improper rotations in the two-dimensional plane is made up of two disconnected pieces. Each one is connected. The piece containing the identity is this one, SO2. The rest is what I have written in the second curly bracket. So what is the manifold of this group? What is the group space? What would you say it is? Huh? That's the definition of the group. Yesterday I said the manifold of this group can be thought of as the circle S1. Circle in a plane. So here, what is the manifold of the group O2 in that kind of language? Two circles. Pardon?
Disconnected.
Correct. So the manifold of this is union of two circles. The identity belongs only to one of the two circles, the one corresponding to SO2. Now comes the question, what are the composition, what is the group multiplication rule? Of course, it is given by matrix multiplication. That's why we call it a defining matrix representation. But I just want to write all the rules here once for all. I'm tempted to use a compact notation. Maybe I will bring it in later. So the symbols I'm using, capital A means a proper rotation. Capital B means an improper rotation, determinant -1. So the A's, of course, obey the SO2 law. And A with a B. What is a B? It is a proper with a P symbol on the right. What is P? P is an improper rotation. In the xy plane, x goes to x, y goes to -y, which is why you have a -1 for the determinant. So what would be A alpha, B beta? B alpha plus beta. Lastly, we must ask, what is B beta, B alpha, B beta? Before calculating, do you expect to be an A or a B? Why?
2 times.
The determinant has to be +1. So what will this be? Oh, I should write here also one other. B alpha, A beta. This should be a B. What is it? Do you want to guess? I will write here a few facts which are very useful. You can check these. I want you to check all these things. A of minus alpha is the inverse of A alpha, correct? That is clear. So what is this? B of alpha minus beta. And this last one? A of alpha minus beta. I want you to appreciate something. So, all of this is equation 9. It's a very simple geometrical operation which we have added on to what we had earlier. Determinant -1, improper rotations. But you can see how much more intricate or complicated or interesting the group has become. Let me, in fact, compare the two groups at this point, and you will understand why it is really quite interesting. You might have thought, what is there new to learn about rotations in a plane? Well, there is something new. If you haven't seen it earlier, I think you will find it quite amusing. First of all, is it abelian or non-abelian? Huh? Yeah. Show me why. Give me an example of a relation here which immediately tells you it cannot be abelian. Huh? Which one? This one? Yeah. This also immediately shows you. This also, both. Okay. So in fact, let us write a small table here. This one was abelian. This one was non-abelian. So that was the first statement. So this inclusion, because it is a plane with 2 dimensions, this has happened. Inclusion of improper rotation has made an abelian thing into a non-abelian thing. Now I will list some things. Since SO2 was abelian, its center, that means the elements of SO2 which commute with everything, consists of everything. Correct? So this is SO2. It's abelian, every element belongs to the center. What about O2? What elements of O2 commute with everything in O2? You're very fast. Did you calculate it or did you see it immediately? You're correct. Very good. Or is it because I'm making such a song and dance about it, you must have guessed? Whatever it is, your answer is right. It consists only of the identity. Identity means in that AB language, what is that element? A of 0. All right? So if this is not clear to anyone, please use these relations, convince yourself. The only element in O2 which commutes with all elements of O2 is a trivial identity element. Classes. What are the classes in SO2? Again, it's abelian. So each element is a class by itself, equivalence class by itself. What about O2? Shall I write the answer or allow you to calculate? What do you want to do? It's quite amazing, the results. Non-intuitive. I'll write it here. Of course, always the identity element is a class by itself in any group. That is one. Then another is these pairs of proper rotations by amount alpha and minus alpha, namely the inverse. I think I have written it here. You can see from this relation, P A alpha, P inverse is A of minus alpha. So the element P, which by the way is a member of the group O2, B of 0, when you take an A, conjugate with P, you get the inverse of that A, which is why A alpha and A of minus alpha are in the same called equivalence class.
So that is A of minus alpha or B of minus alpha?
Which one?
E A alpha is equal to.
Which one? This one?
Yeah. Because on left hand side determinant is negative.
Yeah, here also it is negative. There's a P.
Okay, I thought it's question.
Question mark? No. Sorry. Yeah. Very good question. All right. Okay. All right. And what do you think is the other equivalence classes? You have to do some calculation. I leave this as a study. Whole of next week I am not here. You must do this. Quite surprising. The set of all improper rotations make one equivalence class. Let me leave it. I will not show the proof. It's very, very elementary, but you must do it. Okay. Then the commutator subgroup. Remember what that is? You take pairs of elements and form this combination A, B, A inverse, B inverse. Take products of such commutator elements any number of times, see what you get. In the case of SO2, what is the identity? Because it's abelian. Now, in the case of O2, small a can be a capital A or a capital B. Small b can be a capital A or a capital B. Whatever choices you make, you can see that what you get on the right will be determinant equal to plus 1. It cannot be minus 1. I leave this as an exercise for you to show that the commutator subgroup for O2 is SO2. See, in every respect, how much change there is. Therefore, we can say SO2 is an invariant subgroup in O2.
Okay, B alpha and conjugate by P.
Yeah. Beg your pardon?
You take B alpha
Yeah.
and conjugate by P.
Yeah.
That gives you get B minus alpha. For the same reason that B alpha goes to
Yeah, this is not conjugation. A, B, A inverse, B inverse.
No, the classes are conjugate.
Yeah.
So B alpha and B minus alpha are an equal class.
All alpha.
All alpha. All of this is one class.
Oh,
Here it is each alpha, here it is all alpha. And so, yeah, I should have clarified that. The set of B alpha for all alpha is one class with infinitely many, continuously infinitely many elements. All. Not each, but all. Correct.
The above thing is
Huh?
infinite number. The above thing is the infinite number of classes, each with 2 elements.
Yeah, continuous infinity of classes, each with 2 elements. Here, one class with continuously infinite elements, whatever way you like. But you see how many different things are coming out. This is such a simple example, O2. What could have been simpler? So, SO2 is an invariant subgroup of O2. Therefore, O2 is not a simple group. It has a non-trivial invariant subgroup. You can take the quotient O2 over SO2. What will be that group? How many elements will it have? 2 elements. Unity and one more. And what will be the multiplication law? The square of the second must be identity. Okay? So you can represent it as 1 and P. Okay. Now we come to the, so I hope you agree. This is quite an instructive example. It's so simple but surprising. Now the question is, what do the representations look like? The unitary irreducible representations. No derivation, I will just describe the results. The pattern of the UIRs for the group O2. So they will not all be one-dimensional. Actually, for m equal to 0, that is the trivial representation. One-dimensional, every group element is represented by number 1. think equation 10 has got submerged somewhere, doesn't matter. Then what are the remaining irreducible representations? For all integers greater than or equal to 1, we have one. For each m, we have one representation, irreducible, and I have to write the matrices of the different elements, and here they are. So all of these are two-dimensional unitary irreducible representations, and this is a complete set. So I will leave it as an exercise for you to do the following. Define the space of all square integrable functions on the group O2. What will it mean? Two functions of an angle running from 0 to 2 pi, f1 of alpha and f2 of alpha, a pair of functions, each defined over the circle and finite norm, etc. That will be the space of the regular representation of O2. Okay, and I would like you to work out, to write out what it means to say that any square integrable function of O2 can be expanded uniquely in terms of these representation matrices. Remember now, these are all non-trivial. They are 2 by 2. They are not, this is not the ordinary Fourier series. It is related to the usual Fourier series results, but it follows the pattern of the structure of the group O2. So I leave it as an interesting exercise. Which of these, now what is the, how do you recognize the defining representation of O2 in this picture? Which one is it? Do anyone want to guess? For SO2, we said the defining representation, it is reducible in the complex sense, and it was dm equal to 1 plus dm equal to minus 1. Here what happens is the defining representation is in terms of real matrices. These all are complex matrices. Any idea what the connection is? Which of these is this one? That defining representation is the m equal to 1. It is equivalent to it by a fixed unitary transformation that can be brought into this form. That is the point. Okay? So it is not, as it stands, it is not in this form, but it is equivalent to the m equal to 1 representation. Okay. So this was the discussion of this group. Now it is time to go to more dimensions. Any questions or comments about this? You should work these things out. You should derive that these are the irreducible representations and so on. The algebra is quite nice and slightly non-trivial. Okay. So the reason why this O2 group compared to SO2 has some of these unexpected features, you might say, is the following. The transformation in the plane x going to minus x, y going to minus y, it is reflection through the origin in the plane. That is true. But it is achieved by a proper rotation. 180, huh? Bigger pardon, I can't hear. 180 degree rotation. So, and that happens because the plane is two-dimensional. it would happen in any even dimension, even in 4 or 6 dimension, change of sign of all the Cartesian coordinates is a proper operation, proper rotation. But in odd dimensions, situation will be different. So now let us turn to SO3. This will be a much longer story. It will be very interesting. And of course, you have studied this group in classical mechanics, in quantum mechanics, quantum theory of angular momentum, and so on. And it is sufficiently non-trivial that many, many new features will come in. So this section which I am going through now is a kind of a preparation for the later section when we will study the structure and properties of Lie groups and Lie algebras in some detail. Already when we go from SO2 to SO3, new features will come and we will see all of them. So let us start by giving the definition. The definition is easy enough. A must be real orthogonal and determinant must be 1. Now, you can convince yourself that this is non-abelian right from the start. So already there is a difference compared to SO2. That was abelian, this is not abelian. We will see it explicitly in a little while. Here are some other facts which I will leave to you to convince yourself. The only element of SO3 which commutes with all elements is the unit element. So the center is trivial. Again, very different from SO2. It has no invariant subgroups. So it is a simple group. Group multiplication, group composition is given by matrix multiplication, that is understood. The unit or identity element corresponds to the matrix 1, and the inverse of an element is given by the transposed matrix. You all know that if you start with a 3 by 3 real matrix which has 9 matrix elements, and then you ask, how many independent conditions have we put on the 9 matrix elements? I'm sure you have seen they amount to 6 independent conditions. So this is a 3-parameter or 3-dimensional continuous non-abelian. Yeah, I have brought in the word Lie group. 3-parameter, 3-dimensional, continuous, non-abelian Lie group. When I was a student, people used to say that the world of particle physics is ruled by Norwegians. Why? Because the most important concepts are non-abelian Lie groups. Abel was from Norway, Sophus Lie was also from Norway. And just imagine, I think the population of Norway is 3 million or 4 million or some such thing. It's incredible. So now what are the things that we will do now? We will look at physically useful ways of describing elements of this group. That is, we will look at several ways of choosing 3 independent continuous coordinates for labeling group elements. And I do all this because this is so important for any number of physical applications. Then we will look at the structure of the group manifold. Just as we said, the group SO2, the manifold is the circle S1. We will see what the manifold of SO3 looks like. There will be a nice surprise. And many, many other properties. Conjugation, equivalence classes, all these things we will study. So let us now look at ways of describing elements of this group. There are 3 useful ways, and I want to describe each one of them. The first one is called the axis angle parametrization. This is a geometrical fact which again you may have studied. It is somebody or else's theorem. I think it's Euler's theorem, I'm not sure. Every proper rotation, proper because determinant is 1, every proper rotation is a rotation about some axis by certain angle in, let us say, the right-handed sense. So every SO3 element is completely defined by the axis of rotation and the amount or angle of rotation. So I will denote the axis by a unit vector n, the direction of the pointer, and the amount of rotation by an angle alpha. So what we will do is, I will now write down for you a matrix of this kind which completely describes this rotation. And I will give this as an exercise for you to derive this expression. It is not at all difficult, but I want you to do it, and I will not show it to you here. I have brought in the famous Levi-Civita symbol, epsilon JKL. You all know what it is, completely antisymmetric, and epsilon 1, 2, 3 is equal to +1. So I want you to start from this geometrical idea. Here is the axis n with some components n1, n2, n3, a unit vector, and I do a right-handed rotation by amount angle alpha around n, and I want you to convince yourself that that rotation of Cartesian coordinates in 3 dimensions is described by this 3 by 3 matrix. Okay. So I am saying every matrix in the defining representation of SO3 is of this kind for some axis n and some angle alpha. For some purposes, it is simpler to combine the components of the vector, unit vector n. N is a unit vector in 3 dimensions, and it has a x component and a y component and a z component, or 1, 2, 3 components. So they are okay. Huh? Where is the dot product? Is jth component of n, which is some number, multiplying the kth component of n. There is no dot product here. Something is not clear. What is the confusion? This is a vector, unit vector. That is the meaning of this roof, the carrot. So it has an x and a y and a z component, or a 1, 2, and 3. And I'm just calling them as nj. J equals 1, 2, 3. Okay? And L is, of course, summed over. This is the Lth component of L. So if I combine the axis and the amount of rotation into a single vector, I am writing it in another form. This is not correct. I want you to tell me what extra factors I have to put in. Huh? Where? Middle term. How much here? Correct. Okay. So this is another way of writing the axis angle description of a rotation. Now, what ranges should we give to the axis of rotation and the angle of rotation? We will agree that the axis of rotation can be any direction in three-dimensional space. It can point from the origin to any point on the sphere, unit sphere S2. For alpha, what range should I take? What would you guess I should take? Huh? You know the answer. Somebody who doesn't know the answer. I am saying that I may make a rotation by amount alpha, keeping n fixed. In principle, how far can I go? 0 up to 2 pi. However, as you said, it's not necessary to go all the way to 2 pi. What is the reason for that? You look at this expression. See, I'll sometimes use the second form, sometimes the first form. You can see that this part is quadratic in n, and it involves a cosine. This part is linear in n, it involves the sine. So this is a formula which you can easily check. I'll give it a name, a number. A rotation by amount alpha around n is geometrically the same as a rotation about the opposite axis by the amount 2 pi minus alpha. Therefore, if I say that I will allow all possible choices of axis, all points on the sphere S2, what range should I take for alpha? Should I let it go all the way up to 2 pi if I don't want to count everything twice and so on? I want to describe each group element once, if possible. What range should I choose for alpha? You had answered it. 0 to pi. So here are the ranges for alpha and for n. But have we licked the problem? If we make this choice, is it true that we are counting each group element exactly once? No. Why? Huh? I can't. Who is? Yeah. In this equation. Yeah, exactly. In the case alpha equal to pi, let me write it here. What is it? Matrix element jk equal to when alpha is pi? Read it off from here. Put alpha equal to pi here. Here on the right. What do I get? Please dictate to me. Minus? Yes. This term, does it stay or go? This goes, this go. Yeah, and this one? Plus 2 nj nk. And you see it is quadratic in n, which is exactly what you said, that the two are the same. So here is a very delicate problem. We want to try and describe with a suitable set of coordinates all the elements of our group, and if possible or preferably make our description such that each group element is nothing is missed out, but each one is counted once if we can. So what is the manifold of the group SO3? I will now use this second description. I am combining the axis n and the angle alpha into a single three-dimensional vector. So it means here that I am saying I can limit the range of the magnitude of the vector alpha to the range 0 less than alpha or less than or equal to alpha less than or equal to pi. So now I will try to plot for you the manifold of this group. Now, so it is a three-dimensional picture. Why? Because there are three components for alpha. So this three-dimensional picture is not a picture of physical three-dimensional space where rotations are being carried out. This is a fictitious three-dimensional space, the space of the parameters for group elements, or the space of the coordinates for group elements. It just so happens three-dimensional rotations act on physical three-dimensional space. They are also labeled by three independent coordinates. So there is a little bit of room for confusion. So I want you to appreciate this is the fictitious three-dimensional space, not the geometrical space of physical three dimensions. So how shall we plot it? Well, I have a way of drawing a sphere. I hope it is not too bad. It's not too bad. There was a very great Italian painter, Raphael. All of you have heard of him? He was one of the greatest draftsmen of all time. Whenever he went to visit somebody and the person he was looking for was not at home, he would not leave a slip of paper with his name. He would just draw a perfect circle. And then they knew, oh, Raphael had come and we missed him. That was his signature. So I draw a sphere of what radius? Pi. So I can just indicate that pi like this. And I would like to say that each element of the rotation group corresponds to one point in this picture. Where in this picture?
The downward pi is slightly dislocated.
Beg your pardon?
The downward pi should be.
Oh, yeah, you are right. I'm sorry. It should be here. Correct? Thank you. Yeah. So, what is where in this picture does the unit element lie? Which point in this alpha space corresponds to the identity element? Huh? Origin. Magnitude of alpha equal to 0, that means a vector equal to 0. So this is the identity. So let me write E. Then I can say, if I take any element inside this solid sphere, any element in the interior away from the surface, I would have a three-dimensional vector alpha with some direction and a magnitude strictly less than pi. All right. So that will represent some element of the rotation group given by this matrix. I have not run into this problem if I am in the interior of the sphere. So one can say points in the interior of the sphere, I don't know how to indicate, points in the interior, each point represents exactly one element of the group. And any rotation, provided its angle of rotation is less than pi, it lies in the interior of the sphere. So for such elements where the amount of rotation is less than 180 degrees, we have no problem. They are in one-to-one correspondence with points in the interior of this solid sphere. Now we come to the problem on the surface. Supposing I start with a certain axis and I start with 0 rotation, so I am here. Now let this be the direction of the unit vector n, the axis, and I keep making rotations of slightly greater and greater angle. First I make a 10-degree rotation. It will let us say it lies here. It's a group element. Then I make a 20-degree rotation. It lies here. It's another group element. Maybe this is 45 degrees. No, not 45, a little bit more. Maybe 90 degrees. And so on. As I keep increasing the amount of rotation about the given axis, I am getting a family of group elements lying on this line in this picture. At some stage, I reach 180 degree rotation. That is this group element. Clear? But, now I have made an unfortunate slip. Anyway, what that formula tells us is, suppose I had taken the axis minus n, and I had reached angle pi, I would have come here. Our formula says this element and this element are one and the same. There is no difference. In this picture, they are spatially separated, but they are the same group element. I hope you understand this. So this is the axis minus n. That is the axis plus n. So start with the identity, angle alpha equal to 0. Go on gently increasing the amount of rotation, 100, 150, 170, 180, you are at the surface. You could have chosen your axis of rotation this way, minus n, 10 degrees, 15 degrees, 100, 150, 180. These two are the same. In this picture, it looks as though these are two far away group elements. It's not true. They are the same group element. So, and this is true for any choice of n. So it means 108.
Went up to 180 degrees.
Yeah.
Picture,
Yeah.
with same axis.
Yeah. 181. It is about minus n 179. So if you had gone up to 181, it is really just inside the surface here. Same thing. Okay. Beg your pardon? It is very close to the edge here. 182 degrees is like 178 degrees here. Yeah. They are here, near the identity. Yeah. Hold it. Our angle of rotation, we have agreed, will be between 0 and 180. If you want minus 10, I will make it modulo pi, or 2 pi, whatever it is. Okay. So that convention we must follow. So what does this mean? You see that the manifold of the group SO3, let me write it, SO3 manifold is the same as the interior and the surface of a sphere in 3 real dimensions of radius what? Pi, except that what? Diametrically opposite points on the surface, not in the interior anywhere, are, we say, identified. It means identical. So we have to make a combination of this geometrical picture and these matrix expressions to realize that the manifold of this group SO3 is a little bit involved. You cannot avoid the fact that it is a little complicated. It cannot be pictured as the surface and the interior of a solid sphere. In the interior, no problems. One group element, one point in this picture. On the surface, problem. 2 points representing the same group element. So we introduce a rule of identification. And so this is then the manifold of SO3. It is complicated in this sense.
Is it possible to visualize this kind of surface under this rule of identification?
It is impossible. In 3 dimensions, you cannot draw any figure which is nice and smooth, no sudden jumps of any kind, and which continuously and nicely represents elements of the group SO3 one to one. It's impossible. This is the best you can do. But in a little while we'll do something neat in 4 dimensions. You will see there also there is some problem. So, but I want you to appreciate that whereas SO2 as a manifold was S1, namely the simple circle, the Raphael circle in the plane. Yes, you want to say something? So I want you to really spend a little time thinking about this and sort of getting to terms with it, reaching some equilibrium, mental equilibrium, accept this picture. We will come back to it in a little while. The second convenient way of choosing coordinates to describe group elements is called the system of homogeneous Euler parameters, and it is quite neat. What we do is we take the axis angle parameters, and in terms of them we introduce 4 real variables: A0, A1, A2, A3, with the property that the squares add up to 1. All right. So, if you give me 4 numbers A0, A1, A2, A3 such that their squares add up to 1, clearly this set A represents a point on S3, the unit sphere in 4-dimensional real Euclidean space. The surface only, not the interior, surface. That's why it's written as S3. Then you go back to the equation which I just rubbed out. You see that the matrix elements of the rotation matrix take a very neat form. Beg your pardon, just one moment. Huh? We're here. I'm sorry, I didn't follow. I'm writing it in the same way. I am making this change from axis angle to a point on S3. Okay. Because here I have told you how to compute A0 and A3 vector given n and alpha. So this is the way. So now you see, so this is another way of parameterizing elements of the rotation group. But you see that every term in this matrix element formula is quadratic in the 4 A's. So what does it mean? Does it mean that we have a one-to-one relationship between group elements and points on the sphere in 4 dimensions? No. The point A and the little a and the point minus little a give you the same element of the group SO3. So in this picture, what is the group manifold? What is the group manifold? Half of a sphere. Which half? It's an interesting, good attempt, but let us follow it through. Would you like to say we'll take the northern hemisphere? Suppose for a moment you reduce the dimension. Think of the surface of the earth. You are saying what is the space, the mathematical object obtained by saying you take the surface of the earth, surface, not the interior, and you just declare diametrically opposite points are the same. Then you say, yeah, okay, I don't have to take the whole surface of the earth. I can take a hemisphere and I will get a nice picture. So what would you like to take? Northern hemisphere, because we are up here. If you were in Australia, you take southern hemisphere. So we take the northern hemisphere. Have you now a faithful one-to-one picture or description of the space first defined and a hemisphere? Well, if you are above the equator, no problem. But on the equator, what happens? Huh? Yeah. Okay, so then you'll say, all right, I will take northern hemisphere away from the equator. In the equator, I will take only meridian, longitude 0, Greenwich mean, to 180. You can't stop before 180. Have you licked the problem? No, because 0 and 180 are the same. So it is like a piece of scotch tape which gets stuck to your finger. Sometimes you go on shaking it, you wash your hand, it will never leave you. Okay, so this is just to show that there are no cheap tricks to lick this problem. The manifold of SO3 is very intricate. One has to learn to live with it. Okay. So either you can picture it in this way, or you can picture it as it is the sphere S3, and we say the word language in mathematics is modulo identification. Just a declaration. A point on the S3 and the point diametrically opposite shall be said to be the same. Okay. Actually, it is because of dimensions that things become a little complicated. How do you get the circle from the real line? Suppose I had the entire real line, a variable x going from minus to plus infinity. How do I manufacture the circle S1 out of this? I say I will limit myself to a stretch of the real line. Have I got the circle? No. I have to identify. I have to declare this is the same as that. If I do so, turns out one can draw a nice picture for that. And that is the circle. So the circle arises from a finite interval by a process of declaring that the endpoints shall be thought of as the same. This way of drawing it brings those 2 points right next to each other. This kind of redrawing is impossible in 3 dimensions. So that is what I mean by saying, one of you asked, there is no way to draw a nice, smooth, singularity-free figure in 3 dimensions, which will nicely, continuously, and faithfully depict all the elements of the rotation group. But actually, there is some important consequence of this, and let me see, I would like to try and do that today. I think if you don't mind, I will go up to 1, because whole of last week is band. And anyway, today we have started with tea and biscuits, so it's okay. The third description of a very convenient system of coordinates is what is probably very well known to you. It is called the Euler angle description, and it is very useful for problems of classical rigid body dynamics, and it is also extremely useful in quantum theory of angular momentum. And here I note that my nephew gave a talk here last month or 6 weeks ago on something about rigid body dynamics. right? So he might have used this. I didn't ask him what he did in the lecture, but it must have come in. So how are these introduced? I want to give a little bit of background here. This group SO3 contains in it, of course, as a subgroup SO2, but it has many different SO2 subgroups. For every choice of axis n, one can consider an SO2 subgroup consisting of all rotations with that as a fixed axis. So it will mean rotations in the plane perpendicular to n in 3 dimensions. So what will this be? This is a subgroup. It consists of all these 3 by 3 rotations where we keep n fixed. And now tell me, what range should we allow for alpha? 0 to 2 pi. Because why do I have to go all the way to 2 pi? Why did I not stop at pi?
Because SO2 we have 2 pi rotation.
Correct. I am not allowing you to switch n to minus n. I am saying n, let us keep it fixed. So to identify...
You have made vector be a director.
Yeah.
This is also called director, right?
No, it's a very nice point. I will tell you. Others should know. A director is a word used in liquid crystal physics which says a director is a vector without a sense of direction. This way and that way are the same. So here is a very nice phrase for institutions. A director is a headless vector. Very nice one. Literally true. Okay. So how many SO2 subgroups do we have in the group SO3? How many do we have? Yeah, how many, roughly speaking? Do we have an S2 worth of them? No, we have a half S2 worth of them. Because whether I choose, that's why I put plus minus here. So half S2 worth of SO2 subgroups in SO3. If you take n to be the 3 unit vectors in sequence, one after the other, in the 3 coordinate directions, then you will get 3 out of this infinitely many SO2 subgroups. So those are important, so I will just write them out. I will write them here. You should tell me. The SO2 subgroup made up of rotations around the x-axis. What are those matrices? Well, x-axis is not affected. Only y and z suffer a rotation. So I will just write sine, cosine, minus sine, sine, cosine. S means sine alpha, C means cosine alpha. If I say I want to make the rotation around the y-axis, clearly this y coordinate doesn't change. Where do I put C's and S's? Huh?
In all 4 corners.
All 4 corners. Now where shall I put C?
CS minus C.
Yeah, C, S, minus S, C. Please watch out. It is minus sign is here, not there. This is there in the formula. I'm just pointing out. Z-axis rotation. C minus S, S, C. So everywhere I don't write it. C is cosine alpha, S is sine alpha. Okay. At this point, let me bring in the concept of generator matrices. After all, these SO2 subgroups are all abelian. So if you take two rotations about the same axis, their composition means the angles will just add. So it's quite natural to expect that there will be an exponential notation for this. I just want to show this to you. I leave it to you to check it. Whether you take x-axis rotations or y or z, each one of them can be written in an exponential form where Sj is a 3 by 3 matrix, and here is its set of matrix elements. I will leave the algebra to you. For x-axis rotations, you must take exponentials of S1. Just as a sample, somebody tell me, what is this matrix S1 given by that formula? What is the 1, 1 matrix element of S1? 0. 1, 2, 1, 3. Yeah. How do you know so fast? Correct. 2, 1. Huh? 1 is 2. Yeah. 2, 2. 2, 3. Minus I. 3, 1. 3, 2. 3, 3. 0. Similarly, you can write down S2 and S3 also. All of them are pure imaginary and antisymmetric. Therefore, in the language of quantum mechanics, what can we say? They are Hermitian. So, because they are Hermitian and there's an extra I, these are actually unitary 3 by 3 matrices. But they happen to be real also. Why? Because there is an I outside and there is an S's are pure imaginary. So, they are all real orthogonal. And one can easily convince, this I will leave it to you now as a exercise which I want you to do over the coming week. Please make sure that you understand this. So every element of the proper rotation group can be written, the matrix A of our defining representation can be written as an exponential form. These three matrices, S1, S2, S3, are given a name. They are called the generators of the defining representation of the group SO3. I am introducing these here now, and we will come back to it later in the section on Lie groups and Lie algebras. So now the Euler angle description can be given. It is a fact of geometry that every proper rotation can be built up in this way. As, depending on whether you read from left to right or right to left, a theta rotation around the third axis, a psi rotation around the second axis, phi around the third axis. With three such factors and suitable ranges for the variables, you can be sure that you will cover all group elements. You allow theta and phi, the first and the third, to run over 0 to 2 pi, and you take for the middle angle psi only 0 up to pi. That is good enough. This is proved if you go to any classical mechanics book, Goldstein or any other place. You will see how to arrive at this geometrical result, that any proper rotation in 3 dimensions can be written as a product of 3 factors in this way.
So one of those is E1.
No. this is a convention, 3, 2, 3. There is no E1 in this representation. It's not, I mean, that is also a possible description. But for practical convenience, for problems of classical rigid body dynamics, for quantum theory of angular momentum, this is the most convenient way to do it. Okay? So it's good that you asked that question. I just leave it at answer you in
It's
that.
not 1, 2, 3, it is really 3, 2, 3.
Yeah, 3, 2, 3. Yes, yes. Third z-axis rotation, y-axis rotation, z-axis again, or in the other sequence. All right? All right. So please be clear. It is not x-axis rotation is not explicitly used in this construction, in this way of constructing it. So you might say, now don't we have a nice description of the group SO3? It looks like a cube in 3 dimensions. Not cube, what is it called? Rectangular cuboid or something. 2 of the lengths are 2 pi, 1 is pi. So it is it like a loaf of bread? Not quite. It's a 1/4 of a loaf of bread, right? 2 pi, and pi. Is that the manifold of SO3? No, because there are edge problems. It is not true that there is a unique set of angles for every rotation. For most rotations, there is no ambiguity. For most elements of the rotation group, there is a unique theta, a unique psi, and a unique phi in those ranges corresponding to that group element. But there are a few elements, few means not 1 or 2, lower dimensional infinity, for which these angles are not unique. You can see very easily, suppose you take psi equal to 0, the middle factor. Then the other two will combine to theta and to theta plus phi. So those rotations which have psi angle equal to 0, you are not able to say theta is so much and phi is so much. You can only say theta plus phi is so much. So that is why, except for some exceptional rotations of this kind, it's a good coordinate system, but you must be aware it has this problem. So now there are 2 things I want to do, and then I will close for today. One is to go back to the group multiplication law. So a little bit of calculation is involved, and I want to just indicate it and not go into details. What is the group composition law problem? You take a group element, a rotation. Now I am using this axis angle description where I have combined the axis and the angle of rotation into a single 3 vector. So alpha is some vector in this picture, beta is some other vector. So this is one group element, this is another group element. If I were to multiply them, I expect to be able to say their product corresponds to some other axis and angle. So give me any 2 points in this manifold, uniquely they determine the product, some other point in this manifold. So group composition here is described by a set of how many functions? 3 functions taking real values. How many variables inside each function? 6. 3 for one element, 3 for the other. So group multiplication or the group composition law in a chosen coordinate system is described by the appropriate number of functions of appropriate number of independent arguments. So this is what we will use a great deal, this kind of picture in our general discussion of Lie groups. Now I just want to calculate this for the rotation group in a leading order. Suppose I look at rotations of small angle and I keep terms up to quadratic in alpha at the moment. These are simple sine and cosine functions. You can easily take their power series expansions, plug it into the formula for the rotation matrix. You will find it has this form. The dots are for cubic terms and so on. And then I do a similar power series expansion for A of beta. So I assume alpha and beta are two independently chosen vectors somewhere close to the origin in the three-dimensional picture. And I keep up to quadratic terms. You can see without too much difficulty. Look, the leading terms are these. Apart from the unit matrix elements, the first term is linear, then quadratic, and so on. You can guess without too much trouble that the product element A alpha times A beta, the result of multiplying these two matrices, will be a rotation matrix for which the axis angle parameters will be the three-dimensional vector alpha plus the three-dimensional vector beta plus higher order terms. So now what I want you to do, this I will leave as an exercise so that I can complete something else now. I want you to take such an approximation for this factor, similar one for this factor. Multiply the two matrices, similarly for this factor. Retain only terms of the form linear in alpha, linear in beta, and cross terms alpha beta in the quadratic part. Drop all terms alpha squared, alpha squared beta, beta cubed, alpha beta squared. Drop all those. Do it to leading order. I want you to, well, I don't have to put an approximate equality because I put dots. I want you to tell me when I come back that you have found this result. Maybe you will have found it by today evening. It's a very simple matrix calculation, but I want you to sit and do it. Two little elements, two elements close to the identity, given by a vector alpha and a vector beta. The product of those elements corresponds to a third point near the identity. The third point is obtained by taking the vector alpha, adding it to the vector beta, plus correction. The first non-trivial term is the vector product of alpha and beta. If there had been nothing else, one would have said this is an abelian group, right? This is a sure indication it is not an abelian group because it is not symmetric in alpha and beta. Group composition for the rotation group in this description does not amount to adding the vectors alpha and beta. It is more complicated than that, and here is the leading term. So I am not going to do this calculation. I have given you all the elements of it. Take this power series expansion, plug it in here, here, similar thing there, and compare on two sides only terms of these three forms. Linear in alpha by itself, linear in beta by itself, and in the quadratic part, cross terms only, and then you will get this result. So this is one thing I want you to verify. This is in my notes, equation 26. Now I come for the last. Any question about this? Because I'm omitting the calculation. The last one. Oh. Okay. I have in my notes, I have written, we will use the axis angle description for two more purposes. So I will do only one today. and I will stop at that point. Next one will pick up when I come back. So let me now drop this part. What is this application for this axis angle description that I have in mind? It is the question which we already looked at for SO2, the question of the topology of the group SO3. This is actually very, very pretty, very revealing. What do we mean by topology? What I mean here is connectedness. So I want to ask the following question. I imagine constructing a loop in the space of the group SO3, continuous loop with a parameter S, such that it starts and it ends at the unit element. So it means the parameter runs from 0 to 1, let us say, and it begins at unity and ends at unity. Now, suppose I have one such loop at the unity, and suppose I have another loop at the unity, two loops, both starting and ending at the unity. If in a continuous way, without cutting, scissoring and so on, if one loop can be deformed into the other, we say they are equivalent. All right. So let's draw some pictures. I think I will, I will repair this a little bit, if you don't mind, because unfortunately, well, I am no Raphael, and this thing had come out a bit too uncomfortable. Okay, let's go through it quickly. Suppose I take one closed loop like this. Start at the identity. We are not talking of subgroups. We are only exploring the topological properties of the group manifold. You consider this loop. Start at the identity, move continuously, come back to identity. So that's a closed loop. Now I imagine another loop like this. Go like this, come back. Can one be deformed into the other? Yes or no? Yes, everybody can see that. They are also equivalent to this loop, where I go a little further away from the identity. No problem. They can all be deformed into one another. As long as I never touch the surface and I just stay in the interior, all the loops that I can draw can be deformed into one another. All right? And they are therefore all equivalent to the trivial loop. What is a trivial loop? Constant. For all values of parameter, it is unit origin. Now I do something else. So for the loops I have talked about up to now, I have never taken advantage of the identification rule. What was the identification rule? It said this point is really the same as this point. It said this is the same as that. This is the same as that, and so on. So in the loops that I have discussed up to now, where I never touch the surface, I have not utilized or exploited this identification rule. Now I will draw a loop where I use the identification rule, I exploit it exactly once. You tell me how to draw it. What I'll huh?
You go along the vector in cap and then come back.
Go up to some point on the surface, and once you have reached it, you say, I am actually here. So come, jump here, come back. This is a closed loop in the group. It doesn't look closed, but it is a closed loop. Why? Because this picture is not a faithful picture. The picture must be taken with this rule. or diametrically opposite points on the surface are the same. They are the same group element. So here is a closed loop. Can it be shrunk to the constant loop? You cannot do anything to it. You have used this identification rule once. Suppose you say, I will displace this a little bit. What will happen? This will get displaced. Displace more, this will get displaced. If you have made use of this jumping rule once, you can never avoid using the jumping rule by any continuous deformation. All right. So here is a class of loops in which the the identification is used once. They are not equivalent to the trivial loop. They are not equivalent to the loops which lie completely inside the sphere. Then I say, I'll do another thing. I'll go, so this is the first step of my passage. Then I don't come back to the unity. I will make the jump here. Then I will go here. This is the second leg of my journey. Then I'll use the jump again. And then I'll come back. This is the third leg. Huh? It's also a closed loop. But here, how many times have I used the identification rule? Twice. I have used it to jump from here to here and to jump from here to there. This loop, I can shrink it to 0. Why? Because if I move this one, this pair will not be affected, this will move. When I make this coincide with this will coincide with this. And once I do that, I can pull everything inside. So a closed loop starting and ending at the identity, which exploits the identification of opposite points 2 times or any even number of times, they are all equivalent to one another. They are all equivalent to the trivial loop. Any loop which uses this rule an odd number of times, they are in a class by themselves. So what does it mean? The class of closed loops, continuous loops starting and continuous loops in the group space starting and ending at the identity form 2 equivalence classes. Those which can all be shrunk to nothing at all, those which go up to the surface and use the jumping possibility either once or 3 times or 5 times, they can all be transformed into one another. So we say that the group SO3 is doubly connected. This is the technical term, and it describes for you the nature of the space, the manifold of the group. It is, you can see it is a fairly sophisticated notion, and it had to be done carefully. We had to take this fact seriously that diametrically opposite points are not distinct group elements when they are on the surface. In the interior, no problem. So you have to take this fact seriously if you are interested in appreciating the global structure of the space of group elements. A simply connected space is a space in which every loop can be shrunk to nothing. A doubly connected space is a space in which there are 2 classes of equivalent classes of loops, and that is SO3. What was SO2? Infinitely connected. Because for any integer, you can make any number of clockwise circuits or anti-clockwise circuits. All of them are non-convertible into one another. Why? Because 2 dimensions is very restrictive. Now we have a 3rd dimension, but we have this antipodal points identification. Just as a contrast to this, suppose you think not as a group but as a manifold, the sphere and the surface in 3 dimensions. A solid sphere the interior and the surface, and no identification rules. This you can actually picture. It is what, a cricket ball, an orange, anything you like. This is simply connected. Any loop that you draw, you can never make these discontinuous looking jumps, because in that object, this point and this point are not the same. Every point on the surface is regarded as a new point. So the surface S2 is simply connected, that we all know. If you put a rubber band on a Mosambik, it can be slipped off. If you include the interior, still nothing, as long as you don't have any identification rule. It's also simply connected. SO3 is doubly connected, and I think now you can appreciate why it is very difficult to draw any picture in 3 dimensions which in a continuous and a faithful and a nice way represents SO3. We cannot get rid of this problem. All right, so we stop at this point. So I will be back on 9th of October.